So let's start the 8086 interrupt structure. Initially, 8086 in 8086 interrupts can be coming from anywhere, like from the external side or internal side. Now, basically, they are coming from three sources. One is from the hardware part, that is in 8086 pin diagram. All of you have shown that there are two numbers of pins which are called the NMI and INTR. So these two pins are available as hardware interrupts, and there are some software interrupts also which is internally occurred, and the software interrupts are available from 00 to FF, means 256 types of software interrupts are available in 8086 microprocessor. According to the now the difference between 8085 and 8086 interrupt structure is basically in 8085 what was the how many interrupt hardware interrupt pins are available? 5. But in 8086 how many interrupt pins are available? 2. In 8085 how many software interrupts were available? Only 8, RST0 to RST7. But in 8086 how many software interrupts are available? 256. 256 types of interrupts, software interrupts are available. Okay, and another is three sources. From the three sources interrupts can be coming. One is the hardware, another is the software, and another one, the third one is uh, any condition where the result, suppose the any operation result is too large to fit into the destination register, then at that time certain error condition may arise. So to minimize the error condition, you need to implement certain operation which is based on the interrupt signals, like in case of one type of division, or in case of trap signal or trap interrupt is present here. In this case, these two type of situations, some error condition has been created, and now to minimize this error condition we have to write one interrupt service routine so that no erroneous result can be shown on your display. Okay, so there are three sources from where the interrupts can be coming. Now coming to the interrupt processing, how the interrupts can be processed in 8086 microprocessor. So initially uh, when 8086 microprocessor, when microprocessor executes certain instructions, it sequentially executes the instruction one by one in this way. Here is your main program. So look at this picture. This is the main program which is started from this position, and it is executed sequentially one by one. At certain point, if any external interrupt signal is coming and it interrupts the execution, current execution, then uh, processor either resumes the execution or it completes the execution, then go to the interrupt processing. And when it is ready to process, when microprocessor is ready to process some interrupt signal, first what is to be done? It goes to the stack memory location to store the flag register content first initially. Now what is and up to this position, what are the results, or what is the flag conditions, or everything will be stored inside some register and flag register. So all of these must be stored into the stack. Okay, so that when it is coming from or coming after the execution of ISR, it can resume the execution from the point of uh, interrupt. Okay, so that's why it first pushes the flag register onto the stack, then it clears the interrupt flag and trap flag. Now, why you need to clear the interrupt flag and trap flag? Because uh, in flag register in 8086 microprocessor, there are two machine control flags are available to operate the interrupt, and these are interrupt flag and trap flag. Now, trap flag, what is the function of trap flag? Trap flag, basically it is used for debugging purpose. Its single step interrupt mode has been selected if trap flag is being set, or if it is reset, no single step interrupt can be, single step execution can be made. So that's why it must be clear. So you don't need to operate initially to make it single step mode operation. And another is the clear of the interrupt flag. So interrupt flag must be cleared so that if any signal is coming through INTR, that cannot be identified by the processor. So that's why initially, before starting any interrupt service routine execution, you must or microprocessor needs to push the flag register onto the stack, then clear these two flags, interrupt flag and trap flag. After that, it pushes the content of the next instruction code segment and IP, because sequential instructions can be executed one by one. So when suppose in this position one instruction is being executed, and at that time interrupt signal is coming, so after execution of this current instruction pointer must be incremented by one, so that it can be used to point the next instruction address. So the next instruction address must be saved onto the stack. Why? Before executing any ISR, when or after execution of this ISR, the processor must return to the main program. So it is very important to save the next instruction address onto the stack. So that's why uh, before execution of the ISR, it must push the code segment address as well as IP address, so that 20-bit physical address can be generated, and easily microprocessor can identify that address, so that from this position it can be executed sequentially the rest of the instructions. So next instruction segment address and offset address must be pushed onto the stack. Then load the so interrupt service routine. Now after receiving this interrupt signal, microprocessor needs to execute other operation, which is called the interrupt service routine. Now what is interrupt service routine? Now that is another program of more importance or higher priority compared to the main program. So that upon receiving this signal, interrupt signal, that program should be executed, and that program is called interrupt service routine. So routine, it's a one type of program which must be executed according to your requirement of the interrupt signal processing. Now, this ISR must have some segment address and offset address also, because it's another program. So it must be loaded inside the processor, so that processor can generate the 20-bit physical address using the segment address and the offset address. So your ISR segment address, which is stored inside CS register, and the ISR offset address, which is loaded inside IP register, that must be loaded, so that processor can identify the physical address, and it can be started from this position where the ISR is located. Okay. Then so load CS and IP with ISR address. After that, when it is loaded, microprocessor directly starts the execution of the ISR. But before starting the ISR, you must register. You must save the content of the register onto the stack, then perform the actual operation. Okay, so if you have any register, those are used already in your main program, we have to save the content of that register. Okay. So that when it is executed using the same registers, and after that when ISR has been completed, then the content must be popped up from the stack, and it is retrieved in this way, so that the required number of data will be stored into the specified register where it is initially stored. Then it returns to the main program. But at the time, now how this return instruction is executed here, return is used as IRET, return, interrupt return, IRET. Okay, so the last line of any ISR, interrupt service routine, must be IRET, IRET. So interrupt return. So when it is ready to return to the main program, first it needs to pop the IP and CS of the next instruction, from where the next instruction execution will be started. So because you have pushed the code segment and IP of the next instruction onto the stack before execution of the ISR. So when your ISR execution has been completed, you must pop that content from the IP and CS, from the segment address to the IP and to the CS register. Okay, so you have pushed the item as first CS then IP, so that you need to pop it as first IP then CS. Okay, then you have to pop the flag register content, so that every content of your flags will be stored in the same manner. So everything has been configured. Then it comes to the main program, where it needs to be executed for further instructions. Okay, further instruction execution. So in this way, the interrupt will be processed in 8086 microprocessor. Okay. Now, so clear up to this much, everyone? Clear up to this much? Do you have any doubt how interrupt will be processed? If you have any doubt or any queries, you can ask me.
Sir, last line, pop IP and
Sorry, I can't hear you clearly.
I can't understand the last part, sir. Pop IP and CS part.
If you need to push the item onto the stack, you must pop the item, because the stack is operating in last in first out structure. Okay, last in first out. So what you have pushed last, that will be popped first. So before execution of the ISR is the separate program. So before execution of the ISR, you need to save the content, save the address, memory address of the next instruction of your main program onto the stack. So whenever you have completed the ISR execution, you must pop the content from the stack, so that you can go to the same address. Okay, like when you go for your college, you have to remember your home address, okay, in your brain, so that after completing your college so work, after when you have to return to your home, you have to memorize your home address, so that you can go in the proper way, and you can reach to your home safely. Okay, so the same thing, if you can't remember what is the address where you have left it, so you can't reach to your home. Okay, so the same thing is for 8086 or any microprocessor. So if it needs to execute certain another operation, it must be save the next instruction address where it is interrupted. Okay, otherwise it cannot return to the exact address where it is interrupted. That's why push and pop must be executed along with the interrupt signal. Okay, is it clear?
Yes, sir.
Any other question? Any other queries? So if you don't have any confusion, so I will go to the next slide. and that is the interrupt vector table. Okay, now before discussing this interrupt vector table, um, I need to discuss how many interrupts are available. Okay, so after discussing this slide number 5, I will go to the previous slide where the interrupt vector table is presented. Otherwise, you can't understand what is the interrupt and when it is used or where it is used. So that's why initially, so you have two hardware interrupts. You have two hardware interrupts, that is NMI and trap. Okay, so between these two interrupts, NMI, it is the non-maskable interrupt, and INTR, which is simple interrupt request. Simple interrupt request. This INTR is the maskable interrupt, which can be delayed or ignored by any time. But NMI, which is called the non-maskable interrupt, cannot be masked or cannot be disabled or ignored by the microprocessor at any time. So as soon as any signal is coming through the NMI, it must be executed, and uh, if any signal is coming through INTR, then that signal may be delayed, may be ignored by the processor as per your requirement. Okay, if it is needed to execute as soon as it comes, then you have to make a program or make your logic in such way that when it is it is ready to execute it, it will be no problem. Okay, so you can mask or you can ignore the INTR interrupt, but you can't ignore the NMI interrupt signal. Okay, so these are two hardware interrupt signals. Now another software interrupts are it is started from or it is written in this way: uh, type 0 to type 00 to type FFH in hexadecimal number system. Type 00 to type FFH. Total 256 interrupts are available. Individually, type 00 is called, as per this this slide, it is given as the lowest 5 interrupt types are called 00 to 0004, which are called type 0 as divide by 0 interrupt, type 1, which is called the single step interrupt or trap interrupt, type 02, which is called NMI interrupt, and type 03, which is called 1 byte INT instruction interrupt, and type 04, these are overflow. This is called overflow interrupt. Now, coming to this section. Now, these lowest 5 interrupts are processed in this. This is the type 0. It is this is the interrupt vector table. Now, all the interrupts are stored in the memory location. Okay, in some of the memory portion. Where it is stored or how these interrupts can be stored, the addresses, vector addresses, how it is initialized. So it is initialized within the 1 MB memory space, within the 1 MB memory space. So you don't need to, okay, so 1 MB, within this 1 MB memory space, only 1 kilobyte is required to store the entire 256 interrupts. Okay, that's why, and the memory address range is started from 00000 here, 00000 to 003FF. 20-bit address is given, and 20-bit using this address range, you can easily identify it's a 1 kilobyte of memory. So um, in any 8086 microprocessor, the total 1 MB memory, within this memory section, memory portion, the initial 1 kilobyte locations are reserved to store the interrupt vector addresses. Okay, so you have 256 types of interrupts, so you need 256 vector addresses. Now here you have to remember, to store any vector address means it's a one type of address. Vector address means it's a one type of address. So that address should be 20-bit in size. But how 20-bit will be given in this way? Here can be stored. It is stored in this way. First, for every interrupt, like type 0, consider the lower portion. If this portion it is used by the type 0 interrupt, it is reserved for 4 memory locations, that is 00000000001 0000002 Now these 4 locations are reserved for type 0 interrupt. Next 4 locations are reserved for type 1 interrupt, that is 0000042 00007. These 4 locations are reserved for type 1. Then again next 4 locations are reserved for type 2 interrupt. Then again next 4 locations are reserved for type 3 interrupt, and again the next 4 locations are reserved for type 4 interrupt. Okay. Now these are dedicated interrupts which are designed by the Intel. These are specific interrupts. Okay, which can be used by the instruction by the 8086 microprocessor instruction. Then next 27 interrupts are reserved interrupt. These are used for future purpose, like in case of 801, 862, 863, 886 and Pentium, or after that. So these are used for future processors. These are vacant, these are reserved. And next 224 types of interrupts are available for user. Okay, so a programmer can use these interrupts according to their requirement. Okay, so now to store every interrupt, it needs 4 consecutive memory locations. Okay, 4 consecutive memory locations. Like type 0 interrupt, it is called divide by 0 interrupt. Now if type 0 interrupt is given, then within these 4 memory locations, first the IP address of the ISR will be loaded, then segment address of the interrupt service routine will be loaded. So this type 0 interrupt, when it is occurred, it is ready to service the corresponding request signal by storing these addresses of the ISR. So when your ISR is there, so your ISR address must be saved onto this position if type 0 interrupt is occurred. If type 1 interrupt is occurred, then again location number 00005 and location number 00004 and 00005, the 2 consecutive memory locations are reserved to store the IP address of the interrupt service routine. And next 00006 and 00007, next 2 locations are reserved and occupied by the code segment address of the interrupt service routine. So according to your interrupt type, the corresponding ISR IP address and the segment address will be saved onto this interrupt vector table. So when any internally or external signal is generated, it is coming to this vector table, so that the ISR addresses must be picked up from this corresponding memory location, IP and CS. So to access any type of program or data or instruction, you need the segment address. Microprocessor needs the segment address as well as the offset address. So that's why every ISR addresses are stored in this way. First the IP address, then the segment address, and each memory location can store 8 bit of data at a time. So that's why you need 2 consecutive memory locations to store the 16-bit IP address, and again 2 consecutive memory locations are required to store the 16-bit segment address. Using these 2 type of addresses, 120-bit physical address is generated, so that from this position the corresponding ISR will be executed, interrupt service routine will be executed. Okay, so now clear up to this much, everyone?
JNC.
Everyone clear up to this much? If you have any queries, you can ask me.
JNC L1 कॉमन L1 नीचे
Hey, don't talk.
স্যার ওখানে ওভারফ্লো আর রিজার্ভ লেখা আছে ওগুলো স্যার
ঠিক আছে
ওই স্যার টাইপ 04H ভেক্টর
Saurabh and
ওভারফ্লো
Sohini,
আর
don't talk. Saurabh and
তাড়াতাড়ি
Sohini,
হচ্ছিল
don't talk.
এটা কি করলে?
Sohini, don't talk. Okay.
ওটা কি করলে ভাই? এ কি হয়ে গেল?
Sir, sir,
Yes, yes.
রিডু কর একবার।
sir, I'm telling that in that part
কোথায়?
of 0004
এইটা
to
এটা এটা
0007, what is that part is doing?
আন্ডু কর।
It stores the ISR
এটা
address.
কাটো,
Suppose
এখানে কাটো।
INT 01,
ও ঠিক আছে।
INT 01.
ওই দেখো,
The people who is
ছাড়ো
talking
ভাই,
now, please,
কিছু করতে হবে না।
please
বলো।
stop talking.
মুভ
Yes.
বলতে থাকো।
So
মুভ ডিআই কমা 5000 h 5000 h কোথায় গেল ভাই বাকি সবগুলো কি?
Shomik, don't talk.
Yes, sir.
এত তাড়াতাড়ি শেষ হয়ে গেল? দুটো হওয়া উচিত না ভাই?
Memory location 00004
মুভ কন্টেন্ট অফ সিএক্স
00000.
একটু এখানে গায়েব হয়ে গেল কি? তুমি স্কিপ করে দিয়েছো কি?
Okay, so I will go to the next slide, then I will discuss the doubts and the confusion. Okay, after delivering my lecture. Okay, so type 0 interrupt, what is the function of this interrupt? Why it is called so-called divide by 0 interrupt? Like if this type of, it's type 00, so type 00 means if it is uh, given as int 00 in your program, it executes the same interrupt which is called divide by 0 interrupt. Okay, or example, as for example, the condition where it is used automatically. Suppose if you want to perform a division which is 1 divided by 0. Okay, so if 1 divided by 0 is performed, then because of the result which is too large, or some other type of result, or this type of erroneous condition can be arised, so that Microsoft do not stop its execution. So you need to create certain logic so that it will be display uh, anything else except it is stop the execution. Now if all of you have the smartphone calculator, if it is performed 1 divided by 0, what is shown on your display? Either division is not performed, or infinitive is there, anything. Now to show this type of messages, you need to write a program. Okay, so if divide 1 divided by 0 is performed, at that time you need to operate int 00, and according to int 00, some ISR has been written to display the message over your phone, or PC or laptop, anywhere in any output device. So you need to execute the program in this way. The microprocessor will execute continuously for the further instruction execution. It will not stop the execution at that time. If anything, any time this type of condition has been there. Okay, so that's why it is called divide by 0. So something divided by 0 can be always always can be treated in this way. So no garbage or noise result has been shown over your display. Okay, the execution will be smooth, or it is in a sequential manner. So that is the function of int 00 or type 00 or divide by 0 interrupt function. Okay, and after that, if type 01 is there, that is int 01. So every these interrupts are actually you can write it using int instruction. Int, these are software interrupts. You can write it as int, then the number of that interrupt. It may be 00, maybe 01, maybe 02, or maybe ff. Okay, so int 002, int ff, total 256 types of interrupts are there. So the second interrupt, which is called type 01, type 1 interrupt, which is called the single step interrupt or trap interrupt. Now, what is the function of single step interrupt or trap interrupt? It is always used to debug your program, so that every time each instruction will be executed and it gives the result, then it stops the execution and waits for the command from the end user. Okay, so if this type of interrupt has been occurred in the in microprocessor execution, so it will be executed in single step mode, single step execution mode, or it is called the trap mode. Okay, single step execution purpose it is used. The second, then third is the type 02 interrupt, which is INT02 or NMI. It is called the non-maskable interrupt. So you have hardware interrupt called NMI, you have software interrupt called NMI. Okay, so there are two different interrupt. One is the hardware signal is coming from the external side, another is you can create it internally by using the interrupt instruction, using the instruction, and that instruction should be written in this way, INT02. So if INT02 is written, that means you have used the non-maskable interrupt. So if any program is written with respect to this interrupt, or that program is called the ISR. If that ISR is to be executed, if any signal is generated in this type of interrupt is occurred in your program, then the corresponding ISR will be executed at the same time. It cannot be delayed, it cannot be ignored by the processor. So that's why it is called the NMI. But all this you must write the individual ISR routine for individual interrupts according to your requirement. Okay, so you have another type of ISR if type 0 is used, or INT00 is used. If INT01 is used in your program, then another type of ISR will be implemented. Or if INT02 is there, NMI, that will be executed according to your requirement. In this way, the next is the fourth one, which is called the type 03, or it is called 1 byte INT instruction. It is 1 byte INT instruction, or it is called the breakpoint interrupt. It is called breakpoint interrupt. And last day I have told you the programming methods where each program is being ended by one such instruction, which is called INT03. So I have used this interrupt, INT03. INT03 is called the breakpoint interrupt. So it breaks the sequence of your execution. Now, what is the difference between this single step INT01 and INT03? INT03 breakpoint interrupt, the single step interrupt and breakpoint interrupt. So single step interrupt will be executed one time, means every single instruction will be executed and it stops the execution. Then again the next instruction will be executed and stop the execution. It's based on the command by the end user. But here, if you have used the INT03, which is used as your breakpoint interrupt, so it starts the execution from your first instruction to the breakpoint level. All the instruction will be executed, then it stops the execution and gives a result. Okay, so that is the difference between the single step execution, single step interrupt, and the INT03 breakpoint interrupt. Okay, so the next is this is called the IN type 04, type 4 interrupt, or INT04 interrupt, which is called the overflow interrupt. Now, in case of signed operation, if the result is too large to fit into the destination register, then your overflow flag will be set. And if overflow flag will be set, the corresponding service routine will be executed. So the corresponding ISR will be executed based on the interrupt signal, which is called INT04 or type 4 interrupt, which is called overflow interrupt. And that can be written again, another instruction, specific instruction is present to process any overflow type condition, okay, which is called INTO. INTO, that